Go, also commonly referred to as Golang, is a programming language developed at Google in 2007 by Robert Griesmer, Rob Pike, and Ken Thompson. Designed primarily for systems programming, it is a compiled, statically typed language in the tradition of C and C++, with garbage collection, various safety features and CSP-style concurrent programming features added. The language was announced in November 2009. It is used in some of Google's production systems, as well as by other firms. Two major implementations exist. Google's Go compiler, GC, is developed as open-source software and targets various platforms including Linux, OS X, Windows, various BSD and Unix versions, and since 2015 also mobile devices, including smartphones. A second compiler, GCCGO, is a GCC front-end. History. Go originated as an experiment by Robert Griesmer, Rob Pike and Ken Thompson at Google, to design a new systems programming language. With the following desiderata, the new language was to be statically typed, scalable to large systems, be light on the page, support networking and multiprocessing. In later interviews, all three of the language designers cited their shared dislike of C++'s complexity as a reason to design a new language. Language design. Go is recognizably in the tradition of C, but makes many changes to improve conciseness, simplicity, and safety. The following is a brief overview of the features which define Go, a syntax and environment adopting patterns more common in dynamic languages. Optional concise variable declaration and initialization through type inference. Fast compilation times. Remote package management and online package documentation. Distinctive approaches to particular problems. Built-in concurrency primitives. Lightweight processes, channels, and the select statement. An interface system in place of virtual inheritance, and type embedding instead of non-virtual inheritance. A toolchain that, by default, produces statically linked native binaries without external dependencies. A desire to keep the language specification simple enough to hold in a programmer's head, in part by omitting features common to similar languages. See omissions. Frequent criticisms assert that lack of compile time generics leads to repetition or excessive dynamic code. Lack of language extensibility makes certain tasks more verbose. The type system's lack of const or Hindley-Milner typing inhibits safety or expressiveness. The pauses and overhead of garbage collection limit Go's use in systems programming compared to languages with manual memory management. The language designers argue that these trade-offs are important to Go's success, and explain some particular decisions at length, though they do express openness to adding some form of generic programming in the future, and to pragmatic improvements in areas like standardizing ways to apply code generation and reducing garbage collection pause times. Syntax. Go's syntax includes changes from C aimed at keeping code concise and readable. A combined declaration, initialization operator was introduced that allows the programmer to write "hi equals 3" or "s equals some words," without specifying the types of variables. This contrasts with C's int I equals 3, and const char asterisk s equals some words. Semicolons still terminate statements, but are implicit when they would occur at the end of a line. Functions may return multiple values, and returning a result, a pair, is the conventional way a function indicates an error to its caller in Go. Go adds literal syntaxes for initializing struct parameters by name, and for initializing maps and slices. As an alternative to C's three-statement for loop, Go's range expressions allow concise iteration over arrays, slices, strings, maps and channels. Types. Go has a number of built-in types, including numeric ones, booleans, and character strings. Strings are immutable. Built-in operators and keywords provide concatenation, comparison, and UTF-8 encoding and decoding. Record types can be defined with the struct keyword. For each type t and each non-negative integer constant n, there is an array type denoted nt. Arrays of differing lengths are that of different types. Dynamic arrays are available as slices, denoted t for some type t. These have a length and a capacity specifying when new memory needs to be allocated to expand the array. Several slices may share their underlying memory. Pointers are available for all types, and the pointer to t-type is denoted *t. Pointer operations are limited to indirection. There is no pointer arithmetic. For a pair of types k, v, the type map k, v is the type of hash tables mapping type k keys to type 5 values. Hash tables are built into the language with special syntax and built-in functions. Finally, chant is a channel that allows sending values of type t between concurrently running processes. See concurrency. Aside from its support for interfaces, Go's type system is nominal. The type keyword can be used to define a new named type, which is distinct from other named types that have the same layout. Some conversions between types are predefined, and adding a new type may define additional conversions. But conversions between named types must always be invoked explicitly. For example, the type keyword can be used to define the type for IPv4 addresses, which have 32-bit unsigned integers. Type IPv4 address UINT32. With this type definition, IPv4 address interprets the UINT32 value x as an IP address. Simply assigning x to a variable of type IPv4 address is a type error. Constant expressions may be either typed or untyped. They are given the type when assigned to a typed variable. If the value they represent passes a compile time check. Function types are indicated by the func keyword. They take 0 or more parameters and return 0 or more values, all of which are typed. The parameter and return values determine a function type. Thus, func is the type of functions that take a string and a 32-bit signed integer, and return a signed integer and a value of the built-in interface type error. Any named type has a method set associated with it. The IP address example above can be extended with a method for converting an address to a human-readable representation, viz. Is this the 0 broadcast address 255.255.255.255? Func 0 broadcast float 64 type square struct. Note: No implements declaration side float 64 func area. Then both square and circle are implicitly a shape and can be assigned to a shape typed variable. Informal language Go's interface system provides structural rather than nominal typing. Interfaces can embed other interfaces with the effect of creating a combined interface that is satisfied by exactly the types that implement the embedded interface and any methods that the newly defined interface adds. The Go standard library uses interfaces to provide genericity in several places, including the input-output system that is based on the concepts of reader and writer. Besides calling methods via interfaces, Go allows converting interface values to other types with a runtime type check. The language constructs to do so are the type assertion, which checks against a single potential type, and the type switch, which checks against multiple types. The empty interface is an important corner case because it can refer to an item of any concrete type. It is similar to the object class in Java or C#, but with the difference that the empty interface is satisfied by any type, including built-in types like int. Code using the empty interface can't simply call methods on the referred to object, but it can store the interface value. Try to convert it to a more useful type via a type assertion or type switch, or inspect it with Go's reflect package. Because interface can refer to any value, it's a limited way to escape the restrictions of static typing, like void * in C, but with additional runtime type checks. Interface values are implemented using pointer to data and a second pointer to runtime type information. Like some other types implemented using pointers in Go, interface values are nil if uninitialized. Package system. In Go's package system, each package has a path and a name. References to other packages' definitions must always be prefixed with the other package's name, and only the capitalized names from other packages are accessible. IO_Reader is public but beep2.reader is not. The go-get command can retrieve packages stored in a remote repository such as GitHub, and package paths often look like partial URLs for compatibility. Concurrency. Coroutines and channels. The Go language has built-in facilities, as well as library support, for writing concurrent programs. Concurrency refers not only to CPU parallelism, but also to asynchrony, letting slow operations like a database or network read run while the program does other work, as is common in event-based servers. The primary concurrency construct is the coroutine, a type of lightweight process. A function call prefixed with the Go keyword starts a function in a new coroutine. The language specification does not specify how coroutines should be implemented, but current implementations multiplex a Go processes coroutines onto a smaller set of operating system threads, similar to the scheduling performed in Erlang or Java threads. While a standard library package featuring most of the classical concurrency control structures is available, idiomatic concurrent programs instead use channels, which are synchronized FIFO buffers, to send messages between coroutines. Channels are typed so that a channel of type CHAN-T can only be used to transfer messages of type T. Special syntax is used to operate on less than ch is an expression that causes the executing coroutine to block until her value comes in over the channel ch, while ch less than x sends the value x. The built-in switch-like select statement can be used to implement non-blocking communication on multiple channels. See below for an example. The existence of channels sets Go apart from actor model-style concurrent languages like Erlang, where messages are addressed directly to actors. The actor style can be simulated in Go by maintaining a one-to-one correspondence between coroutines and channels. But the language allows multiple coroutines to share a channel, or a single coroutine to send and receive on multiple channels. From these tools one can build concurrent constructs like worker pools, pipelines, background calls with timeout, fan-out, parallel calls to a set of services, and others. Channels have also found uses further from the usual notion of inter-process communication, like serving as a concurrency-safe list of recycled buffers, implementing coroutines, and implementing iterators. Coroutines and channels concurrency-related structural conventions of Go are derived from Tony Hoare's communicating sequential processes model. Unlike previous concurrent programming languages such as Occam or Limbo, Go does not provide any built-in notion of safe or verifiable concurrency. While the communicating processes model is favored in Go, it isn't the only one. All coroutines in a program share a single address space. This means that mutable objects and pointers can be shared between coroutines. See lack of race condition safety below. Suitability for parallel programming. Although Go's concurrency features are not aimed primarily at parallel processing, they can be used to program shared memory multiprocessor machines. Various studies have been done into the effectiveness of this approach. One of these studies compared the size and speed of programs written by a seasoned programmer not familiar with the language and corrections to these programs by a Go expert. Doing the same for Chapel, CILK and Intel TBB. The study found that the non-expert tended to write divide-and-conquer algorithms with one ghost statement per recursion, while the expert wrote distribute work synchronized programs using one coroutine per processor. The experts' programs were usually faster, but also longer. Lack of race condition safety. There are no restrictions on how coroutines access shared data, making race conditions possible. Specifically, unless a program explicitly synchronizes via channels or other means, writes from one coroutine might be partly, entirely, or not at all visible to another, often with no guarantees about ordering of writes. Furthermore, Go's internal data structures like interface values, slice headers, hash tables, and string headers are not immune to race conditions. So type and memory safety can be violated in multi-threaded programs that modify shared instances of those types without synchronization. Instead of language support, safe concurrent programming thus relies on conventions. For example, Chisnell recommends an idiom called aliases XOR mutable, meaning that passing a mutable value over a channel signals a transfer of ownership over the value to its receiver. Omissions. Go deliberately omits certain features common in other languages, including inheritance, generic programming, assertions, pointer arithmetic, and implicit type conversions. Of these language features, the Go authors express an openness to generic programming, explicitly argue against assertions and pointer arithmetic, while defending the choice to omit type inheritance as giving a more useful language, encouraging instead the use of interfaces to achieve dynamic dispatch and composition to reuse code. Composition and delegation are in fact largely automated by struct embedding, according to researchers Schmager et al. This feature has many of the drawbacks of inheritance. It affects the public interface of objects, it is not fine-grained, methods of embedded objects cannot be hidden, and it is static, making it not obvious whether programmers will not overuse it to the extent that programmers in other languages are reputed to overuse inheritance. Regarding generic programming, some built-in functions are in fact type generic, but these are treated as special cases. Rob Pike calls this a weakness of the language that may at some point be changed. The Google team that designs the language built at least one compiler for an experimental Go dialect with generics, but didn't release it. After initially omitting exceptions, the exception-like panic recover mechanism was eventually added to the language, which the Go authors advise using for unrecoverable errors such as those that should halt an entire program or server request, or as a shortcut to propagate errors up the stack within a package. Conventions and code style. The Go authors put substantial effort into molding the style and design of Go programs. Indentation, spacing, and other surface-level details of code are automatically standardized by the GOFMT tool. Go enters additional style checks automatically. Tools and libraries distributed with Go suggest standard approaches to things like API documentation, testing, building, package management, and so on. Go enforces rules that are recommendations in other languages, for example banning cyclic dependencies, unused variables or imports, and implicit type conversions. The omission of certain features tends to encourage a particular explicit, concrete, and imperative programming style. On day one, the Go team published a collection of Go idioms, and later also collected code review comments, talks, official blog posts to teach Go style and coding philosophy. Language tools. Go includes the same sort of debugging, testing, and code vetting tools as many language distributions. The Go distribution includes, among other tools, Go Build, which builds Go binaries using only information in the source files themselves. No separate make files. Go Test, for unit testing and micro benchmarks. Go FMT, for formatting code. Go Get, for retrieving and installing remote packages. Go Vet, a static analyzer looking for potential errors in code. Go Runs, a shortcut for building and executing code. Godic, for displaying documentation or serving it via HTTP. Gorename, for renaming variables, functions, and so on in a type-safe way. Go Generate, a standard way to invoke code generators. It also includes profiling and debugging support, runtime instrumentation, and a race condition tester. There is an ecosystem of third-party tools that add to the standard distribution, such as Go Code, which enables code auto-completion in many text editors, Go Imports, which automatically adds, removes package imports as needed, Check, which detects code that might unintentionally ignore errors, and more.